In this video, we will cover the transfer function and some of the properties of the transfer function as well as the transfer function of electrical networks. The content which we are going to cover are transfer function basics, transfer function of RC and RLC electrical circuits, examples of transfer function. So learning objectives. Student will be able to define the use of transfer function in the control system, able to derive the expression for the open loop and closed loop system, and transfer function of RC and RLC electrical circuits will be defined. So transfer function is the ratio of Laplace transform of the output or response to the Laplace transform of the input or excitation under the assumptions of zero initial conditions. Here the figure shows the general block diagram of system which is having R of t as the input, G of t as the system gain, and C of t as the control output. From this we can write the transfer function G of s is equal to C of s by R of s, where G of s, C of s, R of s are the Laplace domain or Laplace transform of the respective signals. So the properties of transfer function. Transfer function is defined only for the linear time invariant system. It is not defined for the nonlinear systems. Transfer function is independent of the inputs to the system. System poles or zeros can be found out from the transfer function. Once transfer function is known, any output for any given input can be known. System differential equation can be obtained by the replacement of variable s by d by dt, that is from Laplace domain to the time domain. So we'll see the transfer function of closed loop system. For this case, consider the block diagram of closed loop system which you have seen in the earlier lectures. Here from the block diagram we can write an error signal E of s as R of s minus B of s, which can be written as R of s is equal to E of s plus B of s. Again we can write the gain of feedback network as H of s is equal to B of s by C of s, which can be written as B of s is equal to H of s into C of s. Now the gain for the closed loop system can be given as G of s is equal to C of s by E of s, which can be written as C of s is equal to G of s into E of s. Substituting the value of E of s from the equation 1 to the equation 3, we will get C of s is equal to G of s into R of s minus B of s, which can be written as C of s is equal to G of s into R of s minus G of s into B of s. Now substituting the value of B of s from the equation 2 to the 4, we will write C of s is equal to G of s into R of s minus G of s into H of s C of s, which can again be written as G of s into R of s is equal to C of s plus G of s into H of s into C of s, which can be simplified further as G of s into R of s is equal to C of s into 1 plus G of s H of s. Now our intention is to find the transfer function of closed loop system, which is nothing but G of s is equal to C of s by R of s for the open loop system, and for the closed loop system we will define transfer function as C of s by R of s is equal to G of s by 1 plus G of s H of s. Here the plus sign indicates that the system is having negative feedback. For the positive feedback system, the equation will become G of s by 1 minus G of s into H of s. Now we will study the Laplace transform of resistance R. As we know, resistors are time and frequency invariant. Therefore, the transform of resistor is same as the resistance of resistor. Therefore, the Laplace transform of resistor is given as R of s. For the Laplace transform of capacitance C, let us look at the relationship between voltage, current and capacitance in the time domain, which can be written as I of t is equal to C into dV of t by dt. Solving for the voltage, we will get the following integral as V of t is equal to 1 by C integral over t0 is to infinity I of t into dt. Then transforming this equation into the Laplace domain, we will get V of s is equal to 1 by C of s into I of s. Again solving for the ratio V of s by I of s, we will get V of s by I of s is equal to 1 by sc. Therefore, the transform for the capacitor with capacitance C is given by Laplace transform of capacitor is equal to 1 by sc. Now for the Laplace transform of inductance L, let us look at the relationship between the voltage, current and inductance in the time domain, which can be written as V of t is equal to L into di of t by dt. Again, now transforming the above equation into Laplace domain, we will get V of s is equal to SL into I of s. Again solving for the ratio V of s by I of s, we will get V of s by I of s is equal to SL. And thus the transform for an inductance with inductance L is given as Laplace of inductor is equal to SL. Here the Laplace transform of various electrical networks is shown in the tabular form. Here the Laplace transform for resistance R, L, inductance and capacitance C is shown in time domain and S domain by the means of voltage equations. So the transfer function of RC network. Consider the pictorial diagram of the RC network. Here, applying KVL, that is Kirchhoff voltage law, from the input side for the input loop, we will get V of t is equal to Ri of t plus 1 by C integral over 0 is to t I of t dt. Now taking the Laplace transform of the above equation, we will get Vi of s is equal to Ri of s plus 1 by Sc into I of s. Now applying KVL for the output loop, we will get V0 of t is equal to 1 by C integral over 0 is to t I of t into dt. Now taking the Laplace transform of the above equation, we will get V0 of s is equal to 1 by Cs into I of s, which can again be written as I of s is equal to Sc into V0 of s. Now substituting this value of I of s into the equation 1, we will get V of s is equal to I of s into R plus 1 by Sc. After substituting the value from the equation 3 and 4, we will get V of s is equal to V0 of s into Sc in bracket R plus 1 by Sc. After solving for this equation, we will get V0 of s by V of s, which is nothing but transfer function of RC network, as 1 by SCR plus 1. Now we will look for the transfer function of RLC network. Consider the pictorial representation of RLC network as shown in the figure. Here, by taking the Laplace transform of the above diagram or figure, we will get the figure as shown in figure number 2. Now applying the KVL from the input side, that is for the input loop, we will get Vi of s is equal to Ri of s plus SL I of s plus 1 by Sc I of s. Now applying the KVL for the output loop, we will get V0 of S is equal to 1 by SC into I of S. Now from the equation 1 and 2 and solving for the V0 of S by V of S, we will get V0 of S by V of S is equal to 1 by S square LC plus SCR plus 1. So summary, in this video we have seen transfer function and important properties of transfer function, Laplace transform of each network element, transfer function of closed loop system, transfer function of RC and RLC circuits. Thank you.